Okay, this is the first lab for Organic Chemistry 2, and here we are reducing cyclohexanone into the alcohol cyclohexanol. In this video, we are going to go through the pre-lab lecture. Okay, this is what I would do if we were meeting face-to-face before anybody starts the experiment. That's called the pre-lab lecture. In a different video, I plan to show you how to write your pre-lab entry, the information that I expect to see in your notebook when you walk into lab. All right, so there's going to be two different videos. You could take notes in your lab notebook. Again, your lab notebook should be a bound composition notebook, no spirals. And I'm going to suggest that people only write on the right-hand side of the lab notebook. Okay. So let me give us a title. This is just the pre-lab lecture. Pretend that you're in the lab room, and before anyone picks up any glassware, I'm going to give a pre-lab lecture. A lot of people take the notes in their lab notebook or in a separate notebook, but your lab notebook is fine. If you're using your lab notebook, though, you have to number your pages on the upper right-hand side. If you're continuing to use your lab notebook from Organic Chemistry 1, then maybe you are in the 30s, maybe 37. Okay. And then you want to put the date, and today's date is 7/7. Okay. I don't normally check the pre-lab lecture. These are your personal notes, but this is information that I want you to know for the lab final and maybe for any post-lab questions. All right. Hopefully you've read, or you should have read, the handout. It's only one page, and it talks about how sodium borohydride can reduce these three types of functional groups, or these three types of classes of molecules. Lithium aluminum hydride is a little bit stronger, and it can reduce these three as well, whereas sodium borohydride cannot. Your reaction is shown in the box, okay? And what do I want to talk about? I want to talk about the mechanism, because the mechanism is different than it is for lithium aluminum hydride. The mechanism for lithium aluminum hydride was discussed in one of the lecture videos. And simply you deliver a hydride to this carbon, you make the O minus, and then you protonate, and you're done. This is a little bit unusual because one molecule of sodium borohydride will reduce 4 molecules of cyclohexanone. Let me show you the mechanism, and then we could discuss what to do with this kind of odd stoichiometry, this odd ratio. Mechanism. And let's see. We have cyclohexanone. We're going to draw the sodium borohydride like we did the lithium aluminum hydride in the lecture video by presenting one of the hydrogens to this carbon of the carbonyl. Hopefully that's clear. It's a little bit light. So sodium borohydride. So you have 4 hydrogens around boron. This is, this is negative. You could probably guess that because, whoops, we don't have lithium. We have sodium. If you make a mistake, don't white it out in the lab notebook. Just cross it out and correct it. Okay. All of these rules and guidelines you've heard before. Let me just put it here. No pencil in lab notebook. What else? No erasing. And no whiteout or blackout. Okay. For a lab notebook to be, for instance, admissible in a court of law, like maybe there's a patent dispute, or maybe there's a, I don't know, there's someone needs to be recognized for their work. Well, for that notebook to be valid, you can't have anything erased or anything blacked out. You have to see everything that was literally drawn on your lab notebook. I'm going to draw my mechanism arrows with a green pen. We have that. And now, um, what do we do? Oh, here we go. I almost forgot. Instead of putting the pi electrons onto the oxygen, the pi electrons actually are going to the boron. Okay, that's different. We didn't see that with lithium aluminum hydride, but we do see with sodium borohydride. And the product we get, the intermediate we get is this. Okay, so we do have a bond from the oxygen right to the boron. We did deliver this hydride, so there is an H, and you don't have to draw it, but I'll draw it for emphasis right there. You still have 3 other points of reactivity right there. Okay, so that is the first step. Very different. Lithium aluminum hydride would make this an O minus, and then you just protonate it. The thing is, we could do this 3 more times for each of these hydrogen uh, bonds to boron. So what can we say? I don't want to draw it 3 more times. We could say repeat previous step 3 more times. Can you envision what's going to happen? Okay, what's going to happen is you're going to have a boron now with 4 of these used to be cyclohexanones around it. So let me draw the one on the left. Okay, but this hydride can be donated, and then the oxygen of the new cyclohexanone will bond to boron. So we have this. It's going to be crowded, but this is definitely a intermediate in this reaction. Just make sure you have all the oxygens, okay? Make sure your boron is still negative, right? And this, we said, was called a tetraalkoxy borate, or we could just call it what's a borate ester. Let's say, just call it a borate ester. Okay, you don't have to draw the mechanism for this step because it's just repeating what we saw here. The second part of the experiment is to take that borate ester and react it with acidic water to hydrolyze it. How would that work? Well, let's give it a shot. When you mix water with hydrochloric acid, most of the acid will actually be hydronium, and we'll go ahead and take that step there. Well, oh, that's what's going to happen. We are going to protonate the oxygen. And we're just going to protonate one of them. And what do we get? Okay, to simplify things, I'm just going to call this an OR, R for rest of the molecule. Okay, we'll focus on the left side of the molecule. Okay, and this is negative still. Okay. All right. All right. So next, next we're going to have water. Man, my pen. Next we're going to have water come in, and what is it going to do? Okay, it's going to look a little strange, but it is going to be attacking the boron. Okay, so you may say, well, isn't boron negative? Why would oxygen's electronegative attack boron, which is already negative? Well, it's less negative because this bond is being weakened by this attraction to the positive oxygen. Okay. And what do we get? We get this. We get our product, right? Get our product. Plus, we have H2O stuck to boron, and we still have our 3 OR groups. Okay, so I know this is positive. Okay. Sorry about that. So there's one of your cyclohexanols, the product. You're going to repeat now this last 2 steps 3 more times, right? To take care of the other ones. We're not going to worry about this positive, or we're not going to show the mechanism to show what happens. But let me right here repeat previous 2 steps, right? This one and this one 3 more times to take care of the other alkoxy groups. Okay. And if you do that 3 more times, yes, you'll get your product again times 3. So we end up with a total of 4. Okay. Total of 4. And the side product is actually going to be B, and there's going to be 4 OHs, and this will be negative still. Okay. So you do deprotonate, but don't worry about showing that in a mechanism. Yep, it's complicated. And what's the take-home lesson for this is that when you draw your, or when you think about your overall reaction, let's see. We ran this in methanol, MEOH, and we have this. When you think about your overall reaction, you really do react 4 of these cyclohexanone molecules with only 1 of these, sodium borohydride. And the way we could show that, if you want to, is call it equivalence. 4 parts of the cyclohexanone to 1 part of the sodium borohydride. All right, that is the mechanism. All right, now in your Prelab entry, when you draw your what's called a stoichiometry table, and I'll go through that in a different video. I know it's the first time we've done it together. It's going to be important for us to understand this ratio and how to use that ratio to figure out what? To figure out the limiting reagent and the percent yield. So this ratio, the 4-to-1 ratio, whoops, okay, don't scratch it out or don't black it out. This ratio is important. Yikes. For for identifying the limiting reagent, because you don't need as much sodium borohydride now than what you would normally think. You would normally think you would need 4 sodium borohydrides to reduce 4 molecules of cyclohexanone. All right, so let me show you now that calculation. This is still the pre-lab entry. All right. This one's a little bit lengthy because this is the first time we're doing a experiment where we're very concerned about stuff like percent yield, limiting reagent, stoichiometry. As a suggestion, I had a little bit of trouble reading several students' lab notebooks when they were writing on the back of the pages. So the last guideline on this page, I'm going to say only write on right-hand side. don't forget these four bullet points. All right, this is page 37 for my lab notebook. Um, the next right-hand side page would be what, 39? 39. You don't have to redate it, okay? But this is a continuation, the pre-lab lecture. Yeah. Normally pre-lab lectures don't last as long, but again, I'm showing you from step one uh, the mechanism, but also now how to figure out the limiting reactant. Well, let us start with cyclohexanone. Okay, cyclohexanone. Think about actually, before we do this, think about a sandwich. So a sandwich has two slices of bread. Oops, two slices of bread, and maybe one slice of cheese. Okay, you know how to do this intuitively, because if I said we have 20 slices of bread and we have 15 slices of cheese, what is the maximum number of sandwiches we can make? Well, if we use all the bread and have unlimited cheese, I can make 10 sandwiches. But if I have 15 slices of cheese and unlimited bread, since the sandwich only takes one slice of cheese, I could make a total of 15 sandwiches. Did you see what I did? I pretended that when I'm figuring out for each of these ingredients, what if the other ingredient was in excess, right? How many sandwiches can I make with 15 slices of cheese? 15. How many sandwiches can I make with 20 slices of bread? 10, because each sandwich has two pieces of bread. So now when I have these two together, what is the maximum number of sandwiches? I can't make 15 sandwiches because I don't have 30 pieces of bread. You're going to pick the smaller number. And here we're going to conclude that bread is what's called the limiting reactant. We have two ingredients, two main ingredients. We have the cyclohexanone and the sodium borohydride, my bread and my cheese. In this case, we need 4 slices of bread for every 1 slice of cheese, right? We have a 4-to-1 ratio. You know how to do this in your head. How do we do this with actual chemicals and actual amounts and a different ratio? So here we have, oh boy, 5 milliliters of one. This is a solvent, so we're going to assume that it's excess, but 5 milliliters of one. It's a little bit more complicated, right? Because I was hoping they would give me it in grams, but they didn't. 5 milliliters of one. And one, I'm going to make sure that I put on my dimensional analysis, okay, because eventually we're going to switch to how much product we have. We're going from starting material to product. One is the starting material, and it's like this. Now, in literature, when they represent a molecule with a number, they put it in bold. But if you're writing it on a notebook, it's kind of hard to make it bold and make it obviously bold compared to the other characters. So in a notebook, people usually represent bold by putting a little tilde underneath. Okay. Well, what do we need to do? We need to get through what's called the mole bridge, because I want to know how many sandwiches I can make. I have this much bread. I need to know how many sandwiches I can make. But we didn't weigh, right? We didn't weigh the bread. We don't say we have, 400 grams of bread. What we did was we counted the number of slices of bread. So that is moles in our case. It's not grams, it's not milliliters, it's moles. So how do we convert this to moles? We need to first convert it to grams. And let me pick up some data because I need the density, right? Okay, how do I get out of here? Oh my goodness. density, cyclohexanone. Great. Grams, okay, this is not bad. Grams per centimeter cubed, but a centimeter cubed is the same as 1 milliliter, always, right? 1 milliliter of anything has a volume, and that volume is a centimeter cubed. All right, let me show you where I'm going to use that number. 0.95, right? 0.95 grams per, instead of saying centimeters cubed, we could automatically write milliliters. That will cancel out the milliliters. I don't have to put 1 for 0.95 grams of 1 for every 1 milliliter of 1 because the ones will cancel out. I need this one there, though. Now I'm at grams, and I need the molar mass. Okay, let's take a look at the molar mass. Do we have it here? Close. Almost the same number. 98.15 grams per mole. Oh, but I need to cancel out grams. So we're going to inverse it and have moles on top, 98.5 grams. Okay, so here's my pink pen. Cancel, 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 cancel. I have moles of 1, but I really need moles of 2, the product. What do we say about the ratio, though? For every 1 molecule of this, we do get 1 molecule of product. In the mechanism, we had 4 molecules of this, and we get 4 molecules of product. Either ratio is fine because it's equal, either 1 to 1 or 4 to 4. It's the same ratio. I am going to put, though, since I want to emphasize this ratio here, right? Oh, by the way, if this is true, how many equivalents of product do I get? I get 4 equivalents, right? Each one of these turns into a product. Right? So I'm going to use that ratio. So I got to cancel out the 1, right? I got to cancel out the 1. And therefore, I'm going to say for every, on the bottom, for every 4 moles of 1, I get 4 moles of 2. Now you may ask yourself, or you may question, why do I need to do this? Isn't this just 1? Isn't 4 over 4 1? It is, but you want to get in the habit of drawing the mole bridge because I need this. Why do I need this? I need this term to get rid of this one here, that guy. Because now I cross the mole bridge, and now I have moles of not 1, but I have moles of 2. Okay, technically you could cancel out these moles as well. I have moles of 2. So I have moles of sandwiches, right? Because I know that I'm going to need to know percent yield at the very end of the lab, I'm going to weigh my product. So I don't really want moles, I want grams. So here, the last term, you're going to put the molecular weight of the product, cyclohexanol. Oh boy. Yeah, molecular weight. In Gen Chem, they call this molar mass, a cyclohexanol, 100.16. 100.16. And do we want grams on top? We want grams on top because we want to cancel out this mole right here. 100.16 grams per mole. Mole of what? Mole of 2. Okay. So we get rid of that, and what are we left with? We're left with grams of 2. Okay. Calculator. When I do the calculations, I press enter after each operation. 5 times 0.95 equals, divided by 98.5 equals, times 1, okay, so I don't have to do anything with my calculator, times 100.16. So for 5 milliliters of cyclohexanone, if everything goes well, and this is the limiting reactant, I will get 4.83 grams. This is important. Grams of 2. This is important because in the Prelab entry, you would want to put what is expected. Okay. Now, do I know that this is the actual expected amount? Well, it is if cyclohexanone is the limiting reactant. I don't know that. You're going to have to do these calculations for now sodium borohydride. Let us get started with that. 1 gram sodium borohydride. Okay. You will have to read through the whole procedure to just make sure that you don't add any more later, but we don't. Okay, I'm familiar with this reaction. 1 gram of sodium borohydride. 1.0 grams times. Oh, what do I want to do? I gotta give the identity of this. Because again, when we do the mole bridge, that's when you switch identities. See, from the mole bridge, we went from 1 to 2. Here I need to go from sodium borohydride to 2. Molecular weight of sodium borohydride, NaBH4, 37.83. 37.83. Where does that go? On the top or the bottom? For every 1 mole, 30, and my memory, 37.83. 37.83 grams. We could cancel along the way. Now I'm moles of sodium borohydride. The mole bridge. This is so important. If I really got to get rid of this sodium borohydride, and I have 1 mole of NaBH4, what did we discover? From the mechanism, 1 molecule of sodium borohydride can take care of 4 molecules, right? 4 molecules of the starting material. And it will give me, more importantly, 4 molecules of the product. So that's where this mole bridge is so important, because you're making 4 moles of 2. See, you're going to multiply by 4. All right. So again, so important. And let me cancel out a little bit better than I did here. It's not these 2 moles that cancel out. It's these 2 moles that cancel out. Right? And do you see now we have, if we do the calculation, we have moles of 2. Well, we take moles of 2 and we multiply it by the molar mass, and we get grams of 2. So now we could cancel out this and cancel out that. And what are we left with? 2 and grams. Grams of 2. Just like we ended up here. Now, I'm kind of curious about the number to figure out which one's the limiting reactant. Which number is smaller when we did sandwiches? You pick the smaller number because that's the maximum number of sandwiches you can make. 1 times, oops, not times, divided by, yes, divided by 37.83 equals times 4 equals times 100.16. Ooh, 10.60 grams of 2 of the product. Okay? Take a look at my sandwich analogy. I picked the smaller number. So my conclusion, this is really sloppy, is that cyclohexanone is the limiting reactant, and the theoretical yield in grams, sorry about that, the theoretical yield in grams is 4.83 grams. Those are 2 very important conclusions. If I get an actual yield, if I weigh my product at the end of the experiment and I have only 2.4 grams, right, that is the percent yield of only around 50%. Okay. All right, so that is the pre-lab lecture. In another video, I'm going to show you how to do the pre-lab entry, because for all of us, this is the first time we're doing a pre-lab entry where we are concerned about stoichiometry, and we are concerned about theoretical yield and percent yield. That will be in a separate video.